Welcome to the 8th session of Knowledge Graphs seminar. Our topic today is knowledge graphs and machine learning. Our first presentation would be given by Yure. So Hangyu, could we get going with his presentation?
Yeah, sure.
Thank you very much for the invitation to give a talk. My name is Jure Leskovec, and I will be talking about reasoning in knowledge graphs using embeddings. So we are thinking of knowledge graphs as sets of entities connected by different types of relations. So we can think of knowledge graphs as heterogeneous graphs, where multiple types of entities and relations coexist. Facts are represented using triples, head, relation, tail. For example, Alice is friend with Bob, or Paris is a city. And because the knowledge graphs are traditionally notoriously incomplete, a traditional task that has been examined in this area is the task of knowledge graph completion, or also link prediction, which basically the hope is that we can get an incomplete knowledge graph, and then we can use machine learning to insert or predict missing relations that might exist in the graph. So for example, if we have a graph and we know that Barack Obama was born in the United States, then what we would infer is that Barack Obama is an American citizen, or his nationality is American. However, the goal of this work, and what I will talk about to you today, is trying to go beyond link prediction, right? So our goal will be to do complex multi-hop logical reasoning over these types of knowledge graphs. And in particular, our goal will be to answer logical queries over the graph. These logical queries will be a subset of the first order logic with existential quantifier, conjunction, and disjunction. So we can do and or, but we won't be able to do not. So a running example for this first part of the talk will be how would we answer the question, where did all Canadian citizens with Turing Award graduate? If this is the query in the natural language, you could also write it down in logic, where you would say, I want an answer to my query. I will denote an answer with a V with a question mark, and what I want is I want to be able to identify a node V, where I can go from Turing Award node via the Wien relation to the node V, from the Canada over citizen relation to that same node V, and then after I have identified this middle node V, I need to be able to traverse from there to the answer node over the relation graduate. So the subgraph of how to do this is denoted here at the bottom, where Turing Award and citizen of Canada point to the node V, and then from there we can move to the node graduate, and that would be our answer. So for example, if I'm given a very small toy knowledge graph here at the bottom, and I want to be able to answer this query, then basically I could take this question template and try to fit it here on the underlying knowledge graph. And for example, here you can see that University of Edinburgh, Cambridge, and McGill University would be the answer to our query, because you can see how this particular query graph fits or can be matched to the nodes and to the edges of the proper colors, relation types, to identify the answers. However, answering this task in general is hard. First is that knowledge graphs are extremely heterogeneous. There is kind of lack of schema, or the schema is super large. They are full of noise and incompleteness. There might be uncertainty about various types of relations. Knowledge graphs can be massive in size, and we would like to be able to answer this type of complex queries very, very fast. And you can see that doing this kind of template matching and trying to fit the question, the query graph on the underlying knowledge graph might be very time-consuming. So the key challenge in trying to answer this type of logical queries is that big knowledge graphs as well as queries can involve noisy relations as well as unobserved data. So what this means is that some links might be missing, and if some links are kind of strategically missing, there might be no answers to the query. So naive link prediction would perhaps allow us to recover those missing relations, but then the underlying define template matching would be even more complex, because now we have this kind of semi-uncertain links and so on, and this would never scale to anything realistic. So our goal and the method I'm going to propose today and talk to you about today is called Query to Box. And our goal is to use representation learning to map a graph into a Euclidean space and then learn to reason in that space. So basically, as I show down here, the idea is that we'll take the knowledge graph, map it into some set of nodes in the embedding space, and then when a logical query arrives, we will actually reason about the positions in this space and be able to answer the query. And in particular, the idea is the following, right? We will take the knowledge graph at the training time, and we will embed the nodes into some underlying space. Can be Euclidean space, could be hyperbolic space, anything goes. And then for every logical operator, we would like to learn an equivalent spatial operator, so that at the query time, we get an arbitrary logical query. We will decompose it into a set of logical operators that we support, which is and or and exist. And then we will apply a sequence of equivalent spatial operators to essentially embed the query. And then in order to answer the query, all we have to do is a high-dimensional nearest neighbor search, identify the entities that are close to the query, and that will be the answers to our query. And the key insight that allows us to do this is to represent query as a box. So what I mean by this is, rather than to embed nodes and entities into points, we are going to embed them into boxes. And if we think of high-dimensional boxes in this space, then we can define operators like intersection and union as are well-defined over boxes. In a similar way as we are using Venn diagrams to denote intersection, we can define, let's say, the intersection as the physical intersection of the underlying boxes. So what do I mean by this is, basically what I mean by this is that we will embed everything as a box. So an embedding of a entity will be a box of 0 dimension, but we can embed sets of entities into a box. A box has a center and an offset in each dimension. And that's the main kind of embedding object that we will be working with. Now what we need to do is we need to do two things. We need to identify the projection operator. So basically for every different relation type, we want to be able to kind of implicitly traverse an edge in the embedding space. And then what we also want is we want to be able to define logical operators in the embedding space. So in the case of our Canadian Turing Award winners, we need to define the intersection operator, as well as this projection operator that take us over the win relation, citizen relation, and our graduated from relation. So how do we do this? For these projection operators, for every different relation type, we are basically going to learn a box transformation that will basically take a small box or take a box and then kind of learn where to move it and how to increase its size or how to shrink it. So the idea, for example, is if I want to go from a Turing Award box to traverse the win relation to everyone who has won the Turing Award, then I would want to take the Turing Award entity, apply the projection over the win relation, and that would give me the bigger box, and hopefully the entities that are part of this should be inside the box. Or for example, if I have a box already covering Hinton and Benja, and I would like to apply the projection operator graduate, then it would take this Hinton Benja box, move it, and rescale it in such a way that University of McGill, Cambridge, and Edinburgh are covered by this box. So that's the idea of this projection operator, is basically you take a box and you learn how to move it so that the correct entities are enclosed inside the box. Now what we also need to define is the intersection operator. The intersection operator will allow us to take multiple boxes and compute the intersection between them. And basically the way we do this is that the new center will be the weighted average of the centers of the boxes in the intersection. And then we will also kind of shrink the offset because the size of the intersection is smaller than the individual boxes, right? So those are the two operators that we are going to define in the embedding space. So how would the intersection operator work? So if we have a Turing Award winners and we have a Canadian citizens and we have a box represented each, then the intersection of these two boxes would be the new box here denoted by the shaded region, and that would basically allow us to take kind of intersection of two sets. So now let me give you an example how ideally this would work in practice, right? If I would ask where did all Canadian citizens with Turing Award graduate, here I have this dependency graph or the query graph. The hope would be that during the training time we are able to learn the proper embedding of all the entities in my embedding space, so that when, for example, I apply the first projection from the grounded node Turing Award, I cover all the Turing Award winners. When I start with a Canada node, I apply a different projection, a different box operator citizen, I cover all the Canadian citizens in my knowledge graph. Now I want to take the intersection of the two. This is the of the two boxes, so this gives me the shaded region. And now I would like to apply the next operator, the graduated from operator, that would take this intersection box, the shaded box, move it and rescale it in such a way that the entities McGill, Cambridge, and Edinburgh would be covered inside this box. So our goal will be to strategically position or learn the embedding of the entities, as well as to learn these box operators, so that something like this is that we are able to do, and not only we are able to do over the queries and operators we have trained, but we can do this over queries and logical structures we have never seen during training, so that we will truly be able to generalize to new queries. What is to notice here, that basically everything inside the box, that is the answer to our query. So this will be amazingly scalable, because all we have to do is do a couple of basically spatial operators to define the final box, and then we need to do a nearest neighbor query, kind of a high dimensional query, to see what is inside the box, and that's our answer. So far I told you how to handle the intersection. The question is, how do we handle also OR queries, so disjunction? There will be two possible options. One option would be to say, can we kind of find a way how to take an OR or a union of two boxes? And we actually have a theorem where we show that for a knowledge graph with M nodes, to be able to support arbitrary OR type queries, you would need a dimension of M to handle disjunction. So basically the dimension would be the same as the number of nodes in the graph. And that is obviously prohibitively expensive and too big, so we don't want to be doing that. So our idea is that we can take arbitrary query that has AND and OR, and we can transform those queries in what is called disjunctive normal form, which basically means that we can rewrite the query as a disjunction of conjunctive queries, or disjunction of conjunctions. What this means is that basically we can push all the OR operators all the way to the end, so that we can first answer all the AND queries, and then the final answer set is simply the union of the answer entities of each individual conjunctive queries that only contain intersection operators. And this way we can basically answer arbitrary OR queries as well, by basically pushing the union, the OR operation, all the way to the end. So now with that, basically our solution is that for any kind of AND OR query, we transform it to a disjunctive normal form. We first then answer every conjunctive query separately, and then the overall answer is simply the union of answer sets, or the union of entities of the answers of each of the individual queries. And that basically, without loss of generality, allows us to handle both AND and OR. So what are the benefits of our approach? As I will show you in the experiments, there are three benefits. First is scalability and efficiently. This means that we can answer arbitrary queries very quickly, because each one of them can be reduced to a couple of kind of matrix operators, basically moving in the space, and then a single k-nearest neighbor search query. The method is extremely general. We can answer arbitrary queries, arbitrary logical structures, basically even those that we have never seen during training. And then, as experiments will show, this is extremely robust to noise. So basically, the underlying graph over which we train these embeddings can contain a lot of missing and noisy relationships. but our embeddings are robust and we are still able to accurately answer the queries, even though it requires basically traversing missing relations, as I will show in the experiments. So the way we are going to do this is we are going to, how are we going to train the model is that we are going to randomly generate a set of training queries. For every training query, we will have a positive set of examples, which will be set of entities that are answer to the query. We will have a negative set of entities that will be some other random nodes that have the same type of an entity as the answer entities. And now with this, basically our goal will be to find the embedding and the logical operators so that the positive entities are inside the final box and negative entities are outside the final box. The way I try to illustrate the queries here is a single query here on the left. This is just a simple one-step link prediction. The second query is kind of a two-step link prediction. The third one is a three-step path. And then I have an intersection of two relations and an intersection of three relations. And those will be the queries that we will use for training. As you can see, they are quite simple and they have very kind of simple logical structures. The experimental setup we will do will be geared towards really the question, are we able to generalize, right? So the question is, are we just learning how to, in some sense, memorize the answers to individual queries, right? And what we would really like to do, we would like to do more. We would like to learn how to generalize to new queries we have never seen, to new logical structures, and really be able to chain these operators in arbitrary way. So the experiments will focus on the question, does the method generalize to new unseen queries? Does the method generalize to new logical query structures? And can it basically handle missing relations? So how are we going to do this? Our experimental setup will be that we will train our model on the incomplete graph, which means that we are going to determine node embeddings and we are going to learn logical operators on the training graph that has missing edges. But when we are going to answer queries and when we are going to ask what are the correct answers to those queries, we are only going to test on the queries that are not answerable by the training graph, which basically means that the test queries are going to include at least one missing relation. So in order for us to be able to answer these queries, we will implicitly have to impute at least one missing relation. And what is also important is that the query template matching that I kind of motivated at the beginning of the talk is not able to answer these queries because the links need to be imputed, and simple graph traversal will never find these entities that don't have the correct relation towards them. So this means that our experimental setting and experimental evaluation is extremely tricky because every query has missing relations in it, or every query is not answerable on the training graph. We are going to use this on two very standard benchmarks that are widely used by the community. These are two knowledge graphs coming out of Freebase. They have 15,000 entities and then either 1,300 different relations or 237 different relations. We have about, one of the bigger one with 1,300 relations has about 500,000 edges, and the smaller one has about 300,000 different edges. And in terms of training, we are going to train on the simple conjunctive queries. So paths of length 1, 2, and 3, and the intersection queries of intersection of two relations and intersection of three relations. But we are also going to test our system on queries and query structures that we never see during training. So we are going to do cross-validation over the same query structures as we use for training. And then we are also going to test it on these blue query structures that are either unions of different sizes, as well as more complex query structures that kind of include intersections, as well as path traversals. And we are going to compare this to kind of a similar baseline approach, but it won't be, this approach won't be embedding into boxes, but we'll try to embed everything as a point. And in order to be fair, we will give this point-based embedding twice the number of dimensions as we give to the box embedding, because box is defined by 2 points, by the center and the corner, so it's fair to give more representational power to the baseline. And what do we learn? We learned that the performance on training queries increases by 20% if we are using box-based embeddings. We also see that our performance on the unseen query structures is actually quite good. It's 36% better than what point-based methods would allow us to do. And also our generalization to unseen queries that have the same query structure, the same logical structure as the training queries, is also very much better. And one thing to say is here we are evaluating only the entities that are not answerable. So we are asking how often were we able to take this entity with a missing relation and ranking at between the top 3 candidates. So this is an extremely hard task. To kind of complete the talk and give you one more example, I want to walk you how this works on a real embedding of a real knowledge graph. This is the Freebase 15K. So we do this, but then project the points down to a low dimensional space. So this plot here has 15,000 dots, one for every entity in the Freebase knowledge graph. And the query we will be answering is listing all male instrumentalists who play string instruments. So basically the way we will execute this query is to start with a string instrument, traverse a relation of a type is a, so we get from string instrument to a set of string instruments, instances of string instruments. Then we want to go over instrumentalist relation to find all the people who play string instruments. And then at the bottom path is we want to start with the male node. Again, we want to say who are all the instances of males in our data set. And now we want to take all the instrumentalists of string instruments and all the males, intersect them, and that will be the answer to our query. So what I will do now is I will execute this step by step, and I will be showing you to what is happening in the embedding space that we have defined. So first we take the anchor node string instrument. The blue dot is that string, the embedding of that string instrument node. And now we will take this string instrument box and we will transform it using a projection operator and try to cover all the string instruments. And this is what we did. And in this case, it worked perfectly. We cover all 10 instances of string instruments in our data set. So red color is true positive, orange will be false negative, green will be false positive, and gray is true negative. So here we have kind of 100% accuracy. Now that we have a box covering these 10 string instruments, we want to cover all the instrumentalists. So we will take this box and again apply a projection operator, and let's see what this box covers. It covers, in our data set, we have 472 different instrumentalists of string instruments, and you see that we are basically able to cover most of them. These are red dots. False negatives are the orange dots. These are the string instrumentalists who we haven't covered, and we have a few false positives denoted by green dots. But you see that our true positive rate is 98%. So this is now identifying all the instrumentalists of string instruments. Now we want to take all the males in our data set. We start with a male anchor node denoted by the blue dot, and again we are going to now apply the projection operator. We try to cover all the males. We have 3,555 different males in our data set, and as we apply this box operation, we are able to cover 98% of them. So our true positive rate is 97.9. Now that we have the two boxes in our high dimensional space, the box of males and the box of string instrumentalists, we want to take the intersection. So we take the intersection between these two boxes, and the complete graph number of different answer entities should be nearly 400, and we are able to do this with a true positive rate with 99.4%. So it means that basically we were able to answer this query with these simple box operations very, very accurately, and also very quickly or scalably. So this is what I wanted to share with you today. So I wanted to talk about query to box that allows us to take knowledge graphs, embed them in high dimensional space using boxes, and also learn logical operators that now become spatial operators. And now we can take arbitrary logical queries and we can compose them in arbitrary ways. And I show that this generalizes well to unseen as well as extrapolated queries. And we can basically explicitly train for composability, which is quite important. And at the same time, we are implicitly learning how to impute missing relations. So we are able to answer queries in a robust way. What is interesting is that we can both generalize to new query structures where the logical structure is the same, but it includes different relation types, as well as to completely new logical structures and combinations that were never seen during training, which is quite exciting. One last thing I wanted to mention is that box embedding allows us to answer logical queries on knowledge graphs using and or relations, so we can now handle union and intersection. As I said, generalization is quite good. Our current work focuses on supporting other logical relations, and in particular using negation, as well as thinking of other geometric models of embeddings, perhaps distributions that allow us to handle uncertainty as well in a very scalable way. What I want to finish in the last few minutes of this talk is I want to quickly talk about an effort we are having in my group and the broader community about releasing an open graph benchmark, which is an ongoing effort to develop a set of data sets for large-scale realistic machine learning with graphs. We have a data set, we have a website at Stanford, we have a GitHub with code, as well as paper on the archive. What is the problem currently that we as community are facing is that there is a lot of small graphs and a lot of small data sets from just a handful of domains where people are testing and developing new methodologies. You saw that the free-based knowledge graph is actually small. People are doing graph classification with 188 molecules. So the data sets people are using, or we are using as community, are far too small to be able to reliably measure progress. The other problem is because of these papers are using different data sets, so it's very hard to measure progress and very hard to compare data sets or compare different methods. And the other thing is that because there exists no existing predefined splits, everyone is deciding their own splits, which again makes papers or methods uncomparable. So in order to track the progress and identify issues with current approaches, it is critical for our community to develop a diverse and challenging realistic set of benchmark data sets for machine learning with graphs, as well as machine learning with knowledge graphs. So Open Graph Benchmark is a set of benchmark data sets, but much more than that. It's a diverse set of tasks on graphs, from node classification, link prediction, graph classification, knowledge graph completion. It comes with a code base to load graphs, construct, and represent them. It's compatible with popular frameworks like PyTorch, Geometric, and Deep Graph Library, DGL. And it comes with a code base that allows, that takes care of loading the data, partitioning the data, so that the researcher just have to provide the model, and then OGB also takes care of the evaluation and the reporting the results. Right now, we have various different domains. As I said, we have different tasks in terms of tasks at the level of nodes, links, and entire graphs. We are thinking about natural sciences as domains, social and information networks as another domain, as well as heterogeneous knowledge graphs. And then we have different sizes from what we say small, which is around, let's say, 100,000 nodes or less, medium is around 1 million, and then large will be 10 million or more, so that we can also scale up our methods and see how well they perform. As I said, we have released the first set of data sets at ogb.stanford.edu. We have a core development team of people at Stanford, as well as at Harvard and in Europe. And we have a steering committee that is providing feedback and helping us really develop something that will be used by the community. And we are very, very much welcoming feedback as well as any suggestions for data sets to include. So this concludes my talk. Thank you very much. And my students, Hongyu and Weihua, will be very happy to take questions. Thanks a lot.
Thank you, Yure and Hongya. We will move on to our next speaker. Luna, you are up next.
Okay, let me share my screen. Okay, I can get started here. Hi there, this is Luna from Amazon. And then now it is my turn to answer the question, what is the role of knowledge graph for machine learning? So here I want to answer this question according to my experiences at Amazon. So normally when you are asked this question, what is the role of knowledge graphs in machine learning? I guess a lot of you would first come up with the thought, a knowledgeable search engine will return better answers. If you ask Stanford principal with the Google knowledge graph, it will be able to return this name of your principal right away, together with many other information about Stanford University. And then people might also be thinking, a knowledgeable personal assistant gets more things done. If you ask Alexa to play Taylor Swift in the past year, it better knows the list of the songs by Taylor Swift and which year they are from. And then if you are from e-commerce, the first thing you would think about is possibly recommendation. So a knowledgeable recommender will make better suggestions. Here I'm showing a small knowledge graph with Star Wars books, videos, movies, and the characters. And now let's add those things about Star Wars themed products like the clothes, the lamp, the furniture, the decorations. And then with this knowledge graph, hopefully we will be able to decide which character is more important, why people who bought this lamp also bought this chair, what is the trend of Darth Vader lamps, and what would people ask about boys' clothing. So with all of this being said, we are saying the more knowledgeable, the more intelligent. But how to get to be knowledgeable? So we need to absorb knowledge from all sources like a sponge. We need to align information from different data sources to solve the puzzle. We need to separate the wheat from the chaff such that we can know what is correct. And we want to mine the knowledge from the facts so we can gain wisdom. And so the opposite is also true. The more intelligent, the more knowledgeable. So what I just listed for these 4 bullets correspond to 4 big steps in terms of building and using a knowledge graph. The first step is knowledge extraction. The second step is after we extract the knowledge from all different sources, we want to align them together such that we don't have duplicate entities and duplicate relationships. After that, we want to clean up the knowledge so everything in the knowledge graph is correct, is consistent with the real world. And after that, we want to do knowledge mining, and then we want to use the knowledge to support search, question answering, and also recommendation. So here I'm listing the relevant techniques related to each step. For knowledge extraction, this is related to data extraction from the NLP and web community, related to wrapper induction from the database and data mining community, related to web tables from the database community, and also text mining from the data mining community. For knowledge alignment, this is regarding entity linkage. So we merge the entities that refer to the same real world person or movie, and there is research from the database and data mining community. This is related to schema mapping, deciding which schemas are actually talking about the same thing, the same property, and the same semantics. This is research from the database community. This is related to ontology alignment from the semantic web and the data mining community. And also recently there is this work for universal schema, which is also trying to decide the correspondence between the relationships. And this is from the NLP community. For knowledge cleaning, this is related to the work from the database community for data cleaning. This is related to the work from machine learning and the data mining community regarding anomaly detection, and also related to knowledge fusion from the database and the data mining community. And finally, for knowledge mining, this is related to graph mining from data mining community, knowledge embedding, which we just heard a little bit from data mining community, also related to search and question answering from search and NLP communities. So with this, I'm hoping you are impressed by how many different techniques from how many different communities it is involved to build a knowledge graph and use a knowledge graph. So if we need to fill in this blank, knowledge graph is something for machine learning. Absolutely, it is a gold mine. And meanwhile, it is a test bed. It is the place where you can test out all different kinds of machine learning technologies. And next, we will illustrate this using the product graph we are building at Amazon as an example. Before I talk about what is a product graph, let me firstly say who we are. We are from the product graph team at Amazon. There are more than 50 people in the organization, and including 13 scientists, including me. So we have 10 intern students every year. We are either building or contributing to 3 knowledge graphs at Amazon and supporting 20+ applications. So in the past 3 years, the scientists have published 16 papers and 8 tutorials at conferences from many different communities. So our mission in building this product knowledge graph is to answer any question about products and related knowledge in the world. With a comprehensive knowledge graph for products, we hope to improve Amazon search, recommendation, and voice shopping. So at this point, you might be considering, okay, what's the difference between a product knowledge graph and a generic knowledge graph, like the knowledge graph you have already heard about for Google Knowledge Graph, Bing Knowledge Graph, DeepBot, etc. So is it true that product graph is a small piece of generic knowledge graph? Or it is not so small, it is actually a big portion of generic knowledge graph built by Google, Bing, Freebase, etc. Or it's actually not a subset, but actually it is itself and overlapping with generic knowledge graph. So I know people from the audience are looking at ABC trying to find an answer and possibly are thinking, okay, none of this is correct. And the correct answer is this. So nothing should exist if Jeff Bezos does not sell it, right? Okay, so to answer this question, let me show you a very small example knowledge graph for 2 songs. And as we know, a graph has the nodes representing the entities and the edges representing the relationships. And then now let's squeeze it to one side and add the product part. And these are the Amazon soundtracks for those music recordings. And we can see that one recording might correspond to multiple different tracks. And those tracks belong to different albums, have different resolutions, and so on. Here is another example product graph. This is for retail, and we have the 2 bubbles corresponding to 2 tied products. And the green bubbles correspond to the variations with different sizes, different scents. And we see the information about the products. For example, they have the same brand, the same function. They are both in the liquid form, and neither of them is high efficient. And meanwhile, one of them has some extra function, auto remover. Okay, so the right answer is C. A lot of information for generic knowledge graphs, such as movies, music, and a book, they are related to products. And meanwhile, in the product graph, we have information about hard line, the furniture, the electronics, soft line, the clothes, the purse, the shoes, and also consumables, those stuff you put in your bathroom, in your kitchen. And this is unique for the product knowledge graph. Okay, next, I will tell you 10 challenges in building and using a product knowledge graph end to end. And for each challenge, I will tell you why the problem is hard. I will tell you the intuition for solving this problem, and also the key techniques that could help us drive the intuition home. And I will not get time to talk about the details. Instead, I will list the papers we have published in the past 3 years. If you are interested, you're more than welcome to check out the paper. And from those papers, you can also find many other papers related in that area. And my goal is to introduce you to the many, many interesting research problems to build a knowledge graph, and in particular, a product knowledge graph end to end. I want to impress you with the many, many machine learning techniques from different communities that are required for good solution. And also, I want to invite you to use the knowledge graph as a test bed for your research. So if I don't have time to finish all of the 10 challenges, it's not a big deal. Just to come back to resort to these slides. If one day you run out of research ideas, I'm sure you can find very interesting research problems for your research in the knowledge graph domain. Okay, the first challenge is you possibly don't really know what you want to model. And we know that for each knowledge graph, there is this ontology, including all of the product, including all of the entity types and the relationships between them. And the problem is we have a vast unknown space, and you may not know all of the types and the relationships beforehand. So for Freebase, there are 1,500 different entity types, and also 35,000 type relationship pairs. And it is pairs because the number of distinct relationships is much lower. For products, we actually have 100K different product types. And it is hard to know what are all of these product types because that's evolving over time. And in addition, how to organize them into a taxonomy tree. What is the subtype relationship? As an example, from a seller's point of view, he would think of kitchen and dining department and the sports and fitness department. And under each, there is like some particular sub-department, and then we can see chef's knives, bread knife, and the sports and the fitness, we have hunting sub-department, and we have knife sets and hunting knives. For customers or for the buyers, what they want to buy is really just a knife. So under knife, there could be kitchen knife, outdoor knife, and then chef's knife, bread knife, and so on. So what is the right way to organize all of the different types into a taxonomy? In addition, we have more than 5,000 product attributes, and different attributes apply to different product types. And even if they apply, they may not be important for the customers to make some purchase decision. For example, here I'm showing you car seat and almond. For car seat, the #1 important attribute is brand. And then we come to like style, size, and so on. There are attributes that apply, such as usage and barcode, but they are not important for purchase decision. And there are inapplicable attributes like flavor, ingredient, scent. The babies does like, they do eat their, bite their car seat, but nobody would make the decision according to the flavor of the car seat. For element, it is different. Brand becomes number 2 important attribute. Flavor is more important. And on the other hand, we can see that color, scent, usage, this is inapplicable. So how to decide all of the types and all of the applicable attributes or important attributes? The key intuition here is that it is a vast unknown space, but we have a lot of behavior information from both the buyers and the sellers, and we want to leverage that information. How can we find all of the product types? The sellers will mention them in the product titles, and the customers will mention them in the queries. In this example, from this product title, you can see that the type of the product is storage ottoman. And this would require us to apply named entity recognition to extract the types from queries from product titles. And how to organize the types into a taxonomy tree. Again, this could come from the customer information. Customers who search tea could buy green tea, black tea, oolong tea, but customers who search green tea is less likely to buy black tea. And those behavior information can help us to do graph mining and then build the taxonomy. Next, how can we find the attributes that apply to products of a particular type? Again, important attributes, the sellers will mention them in the product titles, descriptions will provide some of the data, and the customers will mention them in queries, reviews, QA, and so on. So this is, again, behavior mining, possibly with the help of graph mining. Okay, now we have the backbone, the ontology, how to fill in the flesh. In other words, how can we get the data? Unfortunately, for some domains, the structured data is actually very limited, and retail is such a domain. This is because retailers are not trained to provide structured information. Instead, they put all of the information in the product titles, bullets, descriptions, which we call the product profiles. And here I'm showing you the structured information they provide for this ottoman. And you can see it's more about weight and assembled height, weight, length. And you would not say, I want to buy an ottoman which is more than 25 pounds. What you care about is the style, brand, color, shape, and so on. So such information cannot be easily got just as the structured data. But the key intuition behind it is they are often encoded in the descriptions, texts, and in the images. So for this product title, using that as an example, we see that it provides the brand information, the material, and also the color. And for material and the color, we can at least verify from the images. So here we need to do named entity recognition or data extraction from the texts. And we also want to do image processing on the images to get such information. Okay, for some other challenges, for some other domains, it's not so bad. We do have abundant structured data. For example, for publishers for books, movies, music, they are well trained to provide a lot of structured information. The challenge here is that different publishers, they will use different format, they will use different schema, and they might refer to the same person in a different way. So the data are heterogeneous. Here, for example, for the IMDb and the Wikidata, these 2 pages, how can we decide whether that's the same actress? And how can we decide born here and the date of birth here are actually the same? Here is another version of the same problem where we already put the data into the graph format. So we want to align the 2 knowledge graphs built from 2 different data sources. We want to decide if we want to merge these 2 entities because that's the same album. And we want to decide if the 2 relationships, length and duration, are the same. So the intuition in solving this problem, it's not too surprising, is trying to explore the neighborhood. And if we want to decide whether 2 entities are the same, they are duplicates, we want to compare all of the neighborhood entities and values. This can be done by entity linkage and knowledge embedding. So for knowledge embedding, you will embed one entity with all of the neighborhood information. And for the similar relationships, we will compare the entity pairs involved in this relationship. This is related to universal schema, schema mapping, and also knowledge embedding. Okay, next challenge. Let's go to the other end of the spectrum. Data everywhere. Yes, I haven't mentioned that on the web, there are a lot of data. And here I want to call for your attention for some special form of data. This is IMDb webpage. And here is another webpage for a famous Indian movie. And here is another webpage for a famous Chinese movie. And you can see that what grasps your attention is not a lot of texts. Instead, it is all of the attribute value pairs put into particular format on the pages. This is called semi-structured websites. And they are big gold mines in the web because each semi-structured website is typically populated using one or multiple giant databases. So there are a lot of data, and that's very good sources to build a knowledge graph. The challenge is you can see that different pages have very different layouts, and so it's hard to train one model for it, one extraction model for it. And even more, they are in different languages, they could be in different domains. And so how to do the extraction at the web scale. So here the key intuition is that there is typically some hidden visual patterns across the different websites. So to illustrate this, I want to show you this Korean website. I don't know how many people in the audience understand Korean, but let's do some guess. So for this Korean webpage, no matter what it is about, what would be the topic, subject, or entity? You might be guessing this. This must be the topic for this page. And what is an attribute or predicate for it? This is a candidate. And what are the values for this attribute? So these are all of the values for this attribute. Are there any other values? This is likely to be another value, even though we may or may not know the predicate, the attribute. So you can see that even though all of the websites look different, there is some underlying clue. And to leverage this intuition, we want to do multimodal information extraction to leverage the visual information. We can do embedding for those visual components, and possibly with the help of graph neural net, because it is natural to use a graph to model the different components on this web page. We want to do OpenIE on the semi-structured data such that we can extract information even if it does not correspond to some existing ontology relationships. And also, one more thing I didn't mention is web tables, those tabular information where we can extract a lot of knowledge. Okay, now let's say we have got a lot of data and put it into the knowledge form, the triple form. And the next question is, how can we decide what is correct and what is not? Here I'm showing you an Amazon page for this chocolate product. And if you look at the flavors and the sizes, and they do not look like what you typically consider as flavors and the sizes. And here is another example about the same actress. IMDb said she was born in 1982, and Wikidata said she was born in 1983. And what is the date of birth for this lady? So for such cleaning or trustworthiness analysis, the key intuition is actually to explore the redundancy of the data. What do I mean? If we look at all of the values for a particular attribute, are they all in the same embedding space? For ice cream flavor as an example, vanilla, chocolate, mango, these are in close embedding space. Hershey's is less so, and the beef, which is valid flavor, but I doubt if anybody has eaten any beef flavored ice cream. So that does not necessarily fall in this embedding space as well. So this is more towards anomaly detection and link prediction. Next, are values across attributes consistent with each other? If we know for this product, the sugar per serving is way above 0, and then it is unlikely it is sugar-free. So this is data cleaning and also link prediction using knowledge embedding. And finally, if we have the same data from different sources, we want to ask if those sources are consistent with each other. And this is the knowledge fusion techniques, where we try to decide the trustworthiness of the data sources and the correctness of the values. Okay, so far we have been talking about how to build, how to develop the techniques for one domain from a few sources, except the web extraction part. But a working solution for this space may not scale up. What if we have millions of data sources? And especially for web knowledge extraction. And what if we have a hierarchy of 100,000 different categories? And for the user behavior information we just mentioned, what if we have it from tens of different applications over many years? So let me use the 100K category as an example to tell you why it is hard to scale up. So this is partially because 100K categories potentially require 100K different models, because different categories have different value vocabularies and use different patterns. Here I'm showing you for a TV and T-box, the size information use different vocabulary and have different ways to be embedded in the product title. And you might think, well, these two are so different. What about similar products? Let's look at tea and coffee. They are sibling nodes in the taxonomy, both under drink. But again, we see the size information look very different. So the key intuition here is to try your best to train a model that's one size fits all, and using the category and like source information as input, and train the attention, use that as a condition. That's a valid way to go. That's an effective way to go. And in addition, try to apply data augmentation so our model could be robust enough. The next challenge is related to the previous one, and that is about the never-ending requirements for training data. Different categories have different characteristics of data. Different sources definitely have different data distribution. And how can we get training data for so many different cases, different scenarios? So here we really need to learn with limited labels. There are many techniques related to this: active learning, weak learning, semi-supervised learning, transfer learning, meta learning. Normally we thought, okay, in industry, the companies are rich and we can get a lot of training data. The problem is the scale is also so big, and we have to learn to train the models with very limited labels, because we just don't have the time and the resources to collect so many training labels. Okay, the next three challenges are all related to how to use a knowledge graph. I guess at this point you are all already like running out of steam, and so do I. So I will be very brief. Challenge 8 is about finding the needle in the hay. When you have a huge and a comprehensive knowledge graph, how can you easily pinpoint the entities that you are looking for, especially if the entities are not mentioned by the name, such as K-Cups Coffee Organic. So how to find all of such products, and if there is no exact match, how do you find related products? And what if there are too many exact match for this? How do you refine the query and provide some shopping guide? So the key intuition here is to understand user needs And we definitely need to understand what the customers are specifying in the query. This is related to query and understanding and entity linking. We need to decide which part of the requirement in the query is critical and which part is less important, so we can do query relaxation. We need to understand if there are too many results, how to narrow down the search results. What is the next question to help the customers make the decision? This is query refinement. Next, the challenge is how to gain insights from the facts. I have shown this at the beginning, and I wouldn't go to the details. And when we have graphs, normally we do random walk. And we know like a page rank is relying on random walk. And our recent experiences is that if we combine that with supervision, we get better results. So for example, we can do graph mining with graph neural net with the supervision from some training data, and that could help us identify important entities, important relationships, and so on, and also important patterns. Finally, can you explain it? So next talk will be related to this, and knowledge graph has been getting a lot of attention in terms of interpretability, explainability, and so on. And you want to explain the some recommendations and some search results. This is something we're still working on, and the key so far is to form paths through random walk. Okay, several takeaways. Knowledge graph is both a gold mine and a test bed for machine learning. And to build and use a knowledge graph end-to-end, this involves tons of research problems, and it needs techniques from many different research areas. At Amazon, we are building a product knowledge graph, and we are using web knowledge extraction to populate Alexa knowledge. So if you are interested, you are more than welcome to contact us for internship and for full-time jobs. With that, thank you very much.
Thank you, Luna, for a fantastic overview of challenges in building knowledge graphs. We will move on to our next speaker. Robert, you're up next.
Thanks.
Robert, you there? Robert, you're still muted. Robert, you're muted.
Okay, I think I finally got it. You
Okay.
hear me now?
Yeah, and feel free to turn your video on if you like.
Let's see. I thought I had it on. Let's see. It says I'm screen sharing. Oh, start the video. There we go. This software is so badly designed. Okay, can you see my screen?
Yes, we can.
All right, well, we're running late, so maybe I'll just jump to my conclusion.
You have plenty of time. We'll give you a full 30 minutes. Don't worry.
Okay, so that's me. I've got degrees, big deal. Right now, I'm working on the DARPA Explainable AI program. I work at the Institute for Human and Machine Cognition in Pensacola, Florida. These are my areas of expertise. I'll skip through that. Appropriate acknowledgement and disclaimer. This is me, not DARPA. My colleagues, Bill Clancy, some of you may recognize his name. He was the developer of heuristic programming. Gary Klein, the developer of the field of naturalistic decision-making, and Shane Mueller at Michigan Technological University, who is a raving genius and a hell of a nice guy. My stance, I'm not a Luddite. I advocate for better technology, keyword better. I have little patience for hype, spin, or word abuse, so I have some things to say about that. I advocate for more training in the history of the disciplines and in philosophy of science. I have some things to say about that. And I advocate for the union of computer science and psychology. I'll have some things to say about that. These are my three main topic areas: the state of the art in explanation, the traps that people are falling into, and then some ideas about some solutions. The state of the art, a lot of word abuse. Heat maps, they have nothing to do with heat. They're not maps. They rely on a rainbow code. Nobody ever gives any thought to whether or not they should use some other color coding. Neural nets don't really have anything to do with the nervous system. I'll have more to say about that later. People refer to things that the machine is paying attention to, or salience of the image, or the things that the machine is seeing. And that's all metaphorical nonsense. Machines can't pay attention to anything, and they don't see anything, not in any human sense. Lots of goofy concepts. Transparency, people use that word a lot when they should say apparency. If something's transparent, you can't see it. Simulatability, ooh, makes me shiver. Semantic interpretability, I mean, why keep inventing more jargon that we don't need? Borrowing terms from ordinary language and then using them in technical meaning that's pretty much orthogonal to the everyday meaning. The word graph and knowledge graphs is an example of that. You're trying to sell knowledge graphs to the general public, to businesses, to government, and most people think of graph, they think of something like a statistical graph, not these diagrams that you show. And so the result is cross-disciplinary disconnects and a confused or misled general public. My favorite example is interpretation versus justification versus explanation. Many computer scientists refer to their interpretations as if they were explanations, and really what they were was the ways in which a computer scientist would justify their architecture to another computer scientist, and they had almost no explanatory value to anybody outside of that discipline. People say a lot of things about explanation and explainable AI, and then they don't cough up the goods. They say, well, we need to understand how the user perceives the explanation, but then the research doesn't do that. Did they use any cognitive probes to study the user's understanding or their mental models of how the AI system actually works? It's asserted that the result of explanation should be end users deepening their understanding, but there's no indication that the researchers ever investigated that. Current systems, of course, do a lousy job of explaining. We all experience this on a daily basis. I watch something on AlphaGo, and then it comes back and it tells me that I'd be interested in these movies. And from looking at those screenshots, I said, I'm absolutely not interested in them. How did it come up with that? I'm not sure I care, really, but still, there's no explanation that's provided. And there's lots of goofball science going on, measuring explanatory efficacy by measuring EEG waves with lots of odd logic, like if one finds greater left hemisphere activity, then the explanation must have been good. I don't know where these researchers came up with that, but they need to go back and study some psychology. Explanation is just a matter of good interfaces. I see that all the time, and it drives me crazy. Statements like words that occur in similar contexts tend to have similar meanings, which is just incredible thing to say. The goal is to generate a natural language statement which is easy to understand and is equivalent to the machine explanation. I'm not sure what equivalence means here, and what machine explanation? Explanation to whom? Another computer scientist? I don't know. So there's lots of confusing stuff in this field, and I try to cut through all of it. One of the main traps is people assume that the property of being explanation is a property of statements or diagrams or any of that, and it's not. It's an interaction between the purported explanatory material, the learner, and their context. And explaining is a process. The standard model is the XAI system creates an explanation, it gets spoon-fed to the user understands it, you're done. And that's the wrong model. We know that from lots and lots of psychological research on explanatory reasoning, how people explain things to other people, how teachers explain things to students, how people explain things to other people. And the user must be able to explore the performance of the AI at its boundary conditions. How does it perform when it's getting odd cases? Why does it get those odd cases wrong? Why does it get some of it right? What are the reasons for that? They have to experience the failure modes and a range of variation of instances, typical instances, atypical instances, non-instances, all of that. And very little research in explanatory and explainable AI is really pushing on that notion. The AI systems, machine learning systems make errors that humans would never make. We can look at this and understand why it might assume that that kid is a clog, but a human being is never going to make that mistake. And so people come to realize that the AI, it doesn't have human concepts. There's no human meaning in the identifications that a machine learning system comes up with. It's just associating, ultimately, it's just associating patterns of pixels with letter strings. And the way it's described by the computer scientists is very misleading. The example of the foot, a machine learning system that was very, very good at recognizing pedestrians walking along sidewalks. And what they realized was really what it was doing was recognizing somewhat rectangular shaped things toward the bottom of the image. And this is reminiscent of the very first attempt at implementing this sort of technology back in the 70s. Oliver Selfridge's Pandemonium, which was supposed to recognize tanks, it was actually recognizing the shadows caused by trees. But that's another story. Old wine in new bottles. John Locke, 1968, associative networks, starting with primary qualities and building them up to secondary qualities and abstract qualities. And associationism, based on that model, dominated psychology for decades. The center image from the American Journal of Psychology, 1889, neural networks. They've been around a long time. And on the right, we've got semantic networks, conceptual graphs, concept maps. I must have made thousands and thousands, literally, of concept maps for over 40 years. And so there's a history to all of these things. And so if someone comes along and claims that they've got some marvelous system that does new and wonderful things, I'm always keen to find out what exactly is new and wonderful and whether or not there's a knowledge of history behind it. I'm pleased at the two talks I've already heard this evening to see that there is some interesting things going on with regard to intelligent search, and also some discovery of some of the tough challenges that were previously discovered by people like Richens and Soa and Novak and Alberto Cañas and other people. Expert systems, intelligent tutoring systems. Back in the 70s and 80s, a lot of the problems that are being faced now by the explainable AI community were revealed by people like Bill Clancy and Bill Swarthout, even in their dissertations of what it takes for an intelligent tutoring system to be able to help a user improve their mental model. The AI system needs to have a domain model, a task model, a user model, and the explanation process has to be very, very interactive, more like a dialogue rather than the spoon feeding metaphor. Another trap, again, mentioned this earlier, using terms that are mentalistic but are intended only in a way that's particular to computer science. Knowledge graph that's easy to interpret. Well, it's not easy for me to interpret, so it works well, but only for the person who created the thing. And it would be important for computer scientists to point this out and remember that they're not talking just to computer scientists. Where's the knowledge here? What do those bubbles mean? This is said to add semantics, but the machine has no concept of a tree. Why is the sand green? Where's the graph, if this is a graph? Another trap, what researchers think is a good explanation may not be good to a user. This is a computer science version of the psychologist's fallacy, which was pointed out by William James in 1890, and that is the assumption that other people are going to have the same view of things and the same concepts of things as the scientist. And so users are not necessarily going to have the same theory as you do, and psychologists, including myself, have fallen into that trap many times. So some solutions, he said, checking the clock. I've got 10 more minutes. When people ask for an explanation, they don't want to get spoon-fed. They've got a particular question in mind. How do I use this thing? How does it work? What do I do if it gets it wrong? How do I avoid the failure modes? What does it achieve? What can it achieve? What are its limits? How much effort is this going to take? And those are all what are called global explanations that have to do with how this AI system works. And then there are also local triggers. Why did it just do that? How do I make sense of this surprise or anomaly? What should I do differently? What will it do next? What is it trying to do? Why is it doing that? What would it have done if X were different? Why didn't it do Z? And these are what's called local explanations that have more to do with how the AI system made some particular determination or particular decision. And these explanations also must tap into the user's knowledge and their goals. Better support for self-explanation. Most of the explanations that have been put forward, at least until very, very recently, by computer scientists that are supposed to be explanations are really just meaningful to the computer scientists. And they don't really have much explanatory value to other people at all. Matrix of feature weights, for example. A number of people referred to such things as explanations. Well, they're not. I mean, maybe to some people, maybe. But those are people who know the internal guts and how the internal algorithms work at a very deep mathematical level. And your ordinary user isn't going to know that. So when people get these things, they're really just clues or cues. And so the user has to engage in self-explanation, which we do all the time. And in self-explanation, there's some sort of a surprise. And people try to build a story. They try to build a story that gives them some idea of what's going on. And then they ask whether or not, well, does that really make sense? And maybe in some ways it does, but in some ways it doesn't. And so they have to try and resolve that implausibility. And so they'll add new concepts or new principles or new rules, and then engage in another plausibility judgment. And if they get satisfied, then they're done, basically, and they'll go on with their work. And if not, they'll try and think about some other way of explaining it. And this is a model that came from lots of experiments that I and others have done on what happens when people try to explain how complex systems work. Some of the solutions that have been offered: visualizations, text, stories, logical expressions, process models, graphs, networks, tables, extractions, timelines, hierarchies, trees. Some of those have some explanatory value to some people some of the time. Most of them don't have any explanatory value to many people much of the time. So there's a lot of work to be done here. Spoofing, you've all probably seen these sorts of things. My favorite is the one on the right, the Kentucky Fried Poodle. Humans can look at this and see right away what's going on, but these are all things on the left that the machine learning system described as dogs, and things on the right that the machine learning system described as dogs. And the typical response is, well, we just need a bigger training set, but that misses the point. Spoofing like this could be used as a tool to allow people to explore the limits of the machine learning system. And some people are taking this quite seriously, for example, to protect themselves from Big Brother, as this example shows. So people could use the filters and image processing tools to explore what happens to a machine learning system. They could crop out or camouflage regions or features that have a human semantics to them and see if that changes the machine's determination. They could apply the method of difference, which is a experimental logic that comes from John Stuart Mill in the 1800s. I and my colleagues have done some experiments with that. And it's been very, very revealing of the limitations of machine learning systems. And then the method of maximum distance of providing contrast sets, that's sometimes helpful. There was a video that I was invited to look at by Freddie LeCue. Very, very interesting, had a lot of interesting ideas in it. And one that I found particularly interesting, you recall I said a few moments ago that neural nets don't have anything to do with neurons, except the metaphor. But one of the things that we know that people often use to explain things is explanation by analogy. It's been commonly noted in scientific reasoning and reasoning in general that analogy can be very useful and very important. So what if we took that neural network idea and pushed that metaphor for what it's worth? And this was a figure that Freddie LeCue showed, and I find it quite interesting. But you notice down at the very bottom, it's got these little doggies. And that's where it gets misleading, because it implies that the machine has a concept of a dog, and it doesn't. The knowledge graph is over on the right. Again, that's a cartoon. I don't think it's a good idea to show cartoons when you're trying to sell knowledge graphs. Let's see. Okay, some solutions. I and others have been advocating for a shift in the paradigm that's been adopted in the explainable AI research. The current paradigm, the researcher defines the task, whether it's a search task or whatever. The researchers put themselves in the shoes of the user and assume what the user needs. The work is thought of as a set of tasks. The researcher builds a model of the task, and the task is considered independently of the work context. A better paradigm on the right-hand side. The work context defines the user's activity. So what kinds of things do users want to know? What kinds of things do users want to search? Cognitive work analysis reveals what the users really need. And I don't know that cognitive work analysis is being used much in your knowledge graph area, but it might come in handy. Very important thing to keep in mind: in complex cognitive work systems, people do not conduct tasks. This would be a lecture all by itself, and we don't have time for that. The current paradigm, the task is defined independently of the end users, but a better paradigm is to involve the so-called end users from the very beginning, very deeply in the entire design process. In the current paradigm, the task is usually low on ecological relevance, but a better paradigm is define tasks that are highly relevant and ecologically salient. Current paradigm, little or no user testing or usability testing, and what usability testing there is, it's not scientifically robust. Tests for understandability, learnability, usability, usefulness, and trustworthiness are a part of the design process rather than something that's tacked on at the end. The system is evaluated in the current paradigm using computer science analytic methods, sometimes called experiments. But experimentation should be in the authentic work context or life context. Actual user learning and performance should be empirically investigated. In the current paradigm, the to-be created system is thought to be a decision aid, but really it ends up being a process control system. You have to click this and then click that and click that, and then this will help you make a decision, but really it's pushing you along its particular decision tree. A better paradigm, human AI relationship is regarded as one of interdependence, in which the AI complements how humans think, and that's what we refer to as human-centered computing. I've seen some hints of that in the previous talks that we heard tonight, and that's very heartening. I see a need for more integration with experimental psychology on the part of people who are involved in the knowledge graph stuff and people who are involved in the explainable AI stuff. The AI systems must be proved to be understandable, learnable, usable, useful, and trustworthy, and that requires the kind of experiments that experimental psychologists are trained to design and conduct. And some people in the explainable AI community are starting to do that, but there are right ways and wrong ways to go about it. So the wrong way, 5,000 mechanical Turkers and we'll get statistical significance. Not good. The better way is targeted small-scale studies with small n. The love affair with Mechanical Turk, which is something we all have to think more about now because of the need to do distance learning and social distancing. I think doing it by Zoom, where you can emulate the one-on-one psychology laboratory, will be better than just assuming that you can take the easy route and get tons of data from Mechanical Turk. Complex factorial experiments, computer scientists love to jump in and have complex experiments without clearly stated hypotheses, without clear operational definitions of their dependent and independent variables, and all these things that experimental psychologists would insist upon. Lots of mindless statistics, worship of 0.01 and statistical significance. Instead of regarding statistical analysis as a set of exploratory tools, it's taken as a way to escape responsibility for making sound scientific judgments. And the assumption that the users digest and understand the explanations, the wrong way to do it. Need to study users' mental models. Odds are that users will not think about any of this in the same way that you do. And the wrong way, inadequate understanding of the need for control conditions in the experiments. So you need experimental psychologists. How do you operationally define your key concepts? What is an operational definition? Good question. What do you measure? How do you measure it? What are your measurement scales? What are your metrics? What's the difference between a measurement and a metric? Interesting question. This is the explanation process that has been adopted by the DARPA XAI program. You'll see in these yellow nodes in this concept map, I dare say, that there are 4 key points where certain things have to be measured. You have to measure a priori whether or not the explanations are any good, and then measure a priori whether or not the user feels satisfied with the explanations. Then you have to evaluate the user's mental model and test whether or not they comprehend the explanations and comprehend what the AI is doing. And then you have to have some sort of test of performance. I will stop there on time. Thank you. If any of you want any of this goo that I've thrown at you, don't hesitate to contact me. That's my email address. I love to give my stuff away. And much of what I've said here is available in various publications and tech reports.
Thank you, Robert, for that perspective and words of wisdom for all of us. We have about 25 minutes to have a nice discussion about these different perspectives. Maybe I can start off with a question for all the panelists. Maybe I should start off with a question for Robert. Robert, you've talked about concept maps, and you've argued that, well, concept maps have been around for 40 plus years. And one way we could think of the current interest in knowledge graphs is that we are actually trying to build a concept map for the whole web. And the problem is that it's not humanly possible to build it edge at a time. We have to do these operations like entity resolution, entity linking, automatic extraction. So, yeah. I mean, in some sense, you know, yeah, sorry, go ahead, please.
You're dealing with a lot of problems that have come up before in the context of both conceptual graphing by John Sowa and concept mapping by Joe Novak. The diagrams that I've seen tonight are more like Sowa's conceptual graphs, because the linking phrases, the linking relations are constrained to something that's more logical than just unbounded human semantics. But all of those things that you mentioned that are the challenges here are ones that have been discovered and pointed out. I don't know how many times people knocked on my door and said, gee whiz, we need a way to go from free text to a good concept map that we can apply something more powerful than propositional logic to. It would be nice if we could apply first order logics and all those other things and do resolution and cross comparison. We were able to make some headway on some of that with concept maps, and the search capability on concept maps is fairly robust. With CMAP tools, you can search the world literally, because there are many thousands of organizations and tens of thousands of people around the world who are making concept maps. And you can find all the concept maps on particular topics. You can also search them for particular propositions. So we whittled away at that as much as we possibly could. But I'm pleased to see that all these sharp, mathematically sharp people that we've heard from tonight are trying to push that envelope, and I wish you all luck.
Yeah, so as a follow-up to that, I have a question for Luna. You are investing an impressive amount of effort to extract information and structure from things which are very loosely defined. But what if you made a declaration that Amazon can sell your product much better if you give us your data in a structured format? Wouldn't you get immediate cooperation because people want to sell their stuff?
We will get immediate cooperation that people will try to abuse our system.
Why do you say that?
Let me give you an example for abusing the system. So the sellers, they have to provide some basic information such as the brand and the product types. And normally when you put products in a very small type, they will, it is easier for the product to stand out and then somehow be considered even as like best seller. And then, so the sellers will provide some wrongs, very kind of small type, and then they will get the best seller stamp, which they can carry over when they really get appeared in some of the search results regarding their product. So I think you have definitely a good point. Engaging the sellers to provide structured information, this is one good way to go. But meanwhile, it's always important to keep in mind that they may not cooperate in the way that you wish them to, because for them, the thing they really want is to sell their products instead of helping Amazon build the best, most comprehensive and authoritative product graph.
So, Luna, I used to work.
At some level, they are related, because if Amazon has a better product graph, they'll be able to sell their products easier, right?
That's true. We do want to see a good sort of with good information, we get sellers and the buyers more engaged, and then they will provide this better knowledge. We are looking for this sort of spinning off yet, but we are not there yet.
Cool. So I have a comment there. So Luna, I used to work for eBay, and at one point of time, eBay rewarded sellers by giving them free listing if they map to the catalog. So they tried some things like that. So Oren, I have a question for you. Amazon wants to create this most authoritative graph in the world. So you probably have like a huge curation effort. And how do you guys decide whether what's a new product, whether something is a new product or something is an updated product, all those kinds of like curation?
Yeah, so that's a good question. Let me first talk about how to identify a new product or a product that already exists in the Amazon catalog. So we do have some linkage, entity linkage system, and we explore the product titles, descriptions, some structured information, and also importantly, the product image to decide if that's a match. And also, we do ask the sellers to link their product to existing products as well. If we find, hey, this should be a link, a match, but the seller has not provided it for whatever reason, and then we will inform the seller. And if the seller constantly do this, we might even ban the seller.
Okay.
Yeah, but I do want to say one thing. There is curation with no surprise, but on the other hand, curation really does not scale up for products. As I mentioned, we have hundreds of thousands of product types. Even building this taxonomy, we cannot do it just manually. We have billions of products, and every day we have updates for millions of products. Again, that's not something that we can handle with manual curation. So the system we recently developed, and we got a paper about it. We call it self-driving product knowledge collection. It really needs to have a way to guide itself to the important product types and attributes, and train a model that scale up to collect all of the product information.
Thanks.
Thank you.
So Luna, another question for you is, what role do you think these results from psychology or explanations play in the Amazon explanation capability? And as a humorous example, Mike Janasrath, who is an author of a textbook on logic, he was recommended by Amazon that maybe he would like that book and he should purchase a copy of it, right? And the system didn't quite know that, you know, he's the author of the book. So could you sort of speculate on the role these psychological aspects should play on your platform?
Yes, that's a great question. And absolutely, it will play an important role. I think for two things. One is to improve recommendation. So when we recommend something, it's definitely not good to recommend something that is irrelevant, but it is not good either to constantly recommend something that's relevant but very narrow. In other words, we need some diversity. And when people buy things periodically, what is that cadence? And all of this like a purchase behavior, sort of shopping habit, and all of the psychology stuff thing, they need to be considered in recommendation. And then providing a good explanation actually is important. For Amazon recommendation, it is kind of most people know, people who purchase this also purchase that. People who view this also view that. And sometimes we see things that are really a surprise. And we want to say, okay, why people who buy this also buy that? And those things are important. And also, instead of just provide a long list of products where people buy this, also buy that, we might want to put them into good categories. For example, if someone is searching the TV, and then we want to show, hey, these are the TVs that are similar, but have different brands and possibly cheaper. And these are TVs with kind of a more advanced models or higher quality. Information like that will also help people make the shopping decision.
Okay.
Yeah.
So I actually have a general question for students of URE, Vyuha and Hongyu. I mean, personally, I found little difficult to understand how you set up your problem because you're using words like we are going to have a box and we are going to have an embedding. And I mean, I'm sure these words have some meanings, but I was wondering if you can explain what you're doing in a very simple layman's language. Somebody who has basic background in database systems, who they can understand what exactly you're trying to do. What's the problem here?
Yeah, okay, so the problem, so we are machine learning people, so we don't know much about the database, but the problem is that you're given a knowledge graph. You have a lot of facts, and you want to answer a very complicated question, like the Turing Award winner, where does the Canadian Turing Award winner, like graduated from? This kind of complicated question. You want to answer this kind of complicated question.
It's not, why is it complicated? It's a very simple query. Just code it up in SQL and you're done.
And then your knowledge graph is incomplete. So some people may not have like an institution, or some people may not have their nationality in the knowledge graph. So we kind of need to complete the missing edges and answer the complicated query at the same time.
Okay. Okay. So Naren, do we have any audience questions we could take up?
Sure. So we have, so I think the speakers did a very good job in answering the questions offline. There's a few questions that have just come up. This one is about ontologies. I don't know who this is addressed to. Are you aware of the realist ontologies from organizations like BFO? What do you think of these? Anyone wants to address that?
So I know a little bit about BFO, and maybe I can sort of translate that question for our panelists. So BFO is kind of like a upper level ontology where they have distinctions like physical object, non-physical object, very high level, very general distinctions. And one way to reformulate the question would be, would those upper level or high level distinctions play any role in the context of work that each of you is doing?
Okay. Then I think there's a message for Luna. Someone wants to collaborate with them. So I'll let you sort of figure out how you connect.
I do want to also answer the previous question. For ontology honestly is the most surprising part for me, because I thought ontology is fairly easy part because that's only the backbone, and then with the backbone we fill in the data, so there will be much more data points, triples, than the ontology components. But it turns out building a good ontology for a knowledge graph is always the bottleneck. And I'm not too familiar with BFO, and it does not look like it is directly applicable for our work for building product knowledge graph. And I don't think that is used for Google Knowledge Graph either. However, there is all of these questions regarding common sense and kind of relating the sort of real world knowledge graph, generic knowledge graph, or product knowledge graph with those common sense concepts. And there might be something interesting over there.
Okay. So a question for Luna just came in. What are some rough numbers behind the entity resolution that you go through? How many firms, people, products, etc.?
Mm-hmm. So I'm not sure how much I can talk about the data at Amazon. It could go over billions.
Okay. So let's see. I think we are done with
so
all the questions.
One question for students of URE is that, so you are explaining that the technique you have is able to answer queries when the knowledge base is incomplete. So let's say I pose a question to your knowledge graph and your technique comes up with an answer, and the user says that, well, you know, this makes no sense to me. What do you do in that case?
What do you mean? Like, if
Well, again, we are on the topic of explanation, right? So, I mean, the user says, okay, you came up with this answer. Why did you come up with this answer, right?
Mm-hmm. Yeah, I think that's pretty. That's a kind of a research challenge. Yeah, we just give an answer that's based on statistics, right?
Okay.
Like, and then we give answers, but then the research question is how we can explain it. Yeah, currently our method cannot explain the answer.
I mean,
It's
that's not only a challenge for knowledge graph, right? That's also a challenge for all the machine learning community. You can always say that we train a model and the user say, no, the label of this image is not a cat, although your prediction is a cat.
Right.
I guess that's really a challenge for all the communities, not just for our for knowledge graph or not just for our model.
Right.
But we are training the model and do the prediction based on the statistics, based on the information of this neighboring entities, right? In order to predict some links or something like that, right? So we are doing our best, but we cannot say that our model is perfect.
Okay. Okay, so I have a general question for Robert. You know, we have had several talks in this series where people are trying to build web scale knowledge graphs, and either for search application or for data integration application. Amazon, I mean, Luna talked about product knowledge graph. So you are coming in as a psychologist and you say that, well, you know, we've been doing this for 40 years. But if I was one of them, my question to you would be, fine, you've been doing this for a long time. What problem can you help me really solve? Right? So how would you answer that question? Okay, I want to hire you. You know, what would you do for me? Right?
Well, I'm retired, so I'm not hireable. I don't need money and I don't need publications, but it depends on what you find as a problem. In the last part of my talk, I mentioned that there is a role for psychological experimentation, and we just saw it a moment ago when Wei Hua was talking about, you know, it's just statistical, and you pointed out that someone pointed out that that's a general broad issue about machine learning. Well, if you're going to offer something as an explanation, demonstrate somehow that it has explanatory value. And what does that mean? It means that the person who's using it has a better understanding. Well, how do you find out if that's the case? Does it mean that they're performing better? Well, how do you measure that? And those are all things that experimental psychologists can do. I have made some very, very large concept maps, although not nearly in the order of magnitude that is the focus and big struggle of companies like Amazon. And it's non-trivial to make even the concept maps on the scale of complexity that I've made is very, very non-trivial. And so as far as solving problems of resolution and missing values and bringing in some logic and inference engines and all of that, that's not my thing. There are some people at the Institute of Human Machine Cognition who have worked on that, like Pat Hayes. It's a name with which some of you might be familiar. So my answer is it depends on what your problems are and whether or not my expertise would help. There may be some let me not personalize it. A good experimental psychologist, I may or may not be a good one, could help with it, but there would be others that they might not. That's sort of a non-answer to your question.
Well, so, no, I mean, again, I can make my question more specific. I mean, you have very correctly articulated that as computer scientists, we tend to abuse the terminology such as heat maps and machine is seeing things, and you had several examples on those slides. So let's say we agree with you that we are abusing the terminology. what should we be using, right? We are doing our algorithms are doing these interesting things. So how should we describe that?
Yeah, that's a good question. And it would take another slide set to work through the alternatives, and there are some alternatives. But it doesn't take an experimental psychologist to notice when word abuse is going on, although it helps because a lot of the terminology here is mentalistic and terms that are used in ordinary language that are laden with psychological value and meaning, but are being used by computer science in a different way, in a very different way, even the word experimentation for that matter. And so it would help to get, the only thing I say is what you need is somebody with a good radar detector.
Okay, so let's now turn to a broader question, which is again directed to all the panelists, but let's start with Luna. Do you think Amazon's product graph will ever be done? I mean, is this a black hole of a problem, or what's the next where this could just run on its own?
This is a great question. I remember the first time we showed a small demo that's related to the Tide products to our SVP, and he was very happy with the demo. He asked us how we collected the data, and then he said, wow, this is a 100-year project. And you know, since then we have been all like really exercising hard so we can live for 100 years longer. So it is hard. On the other hand, that's kind of why we are trying to develop this so-called self-driving solution. So there are two things. One is it will scale up, it will navigate the space and add new types and models by itself. And second, it will absolutely be human in the loop, at least to do some evaluation. But human in the loop, hopefully, eventually, we're far away from there, but hopefully, eventually, it is a system to decide when a model needs to be trained, when the data scientists need to get involved, when some data labelers will do some annotation, instead of humans really stay there and try to run different stuff. So if we are able to have this self-driving thing successful and then have some human in the loop system controlled by the system, not by the human, then I think we will not need to work for 100 years.
There was a DARPA program some years ago. It was called Rapid Knowledge Formation that tried to do exactly that. And stories can be told of the problems they encountered and why that ended up the way it ended up. We might even cite psych as a 100-year problem that ended up getting so embroiled in all kinds of technical details that it seemed to an outsider to just wither on the vine because it was just humanly insurmountable.
Well, the interesting thing about knowledge graphs is that they are making money. There's a business use case, right, which other systems have struggled to find. But turning over to URA students, what's next for you guys? Where are you guys headed? You guys are muted. If you're speaking, we can't hear you.
Yeah, from here.
Yeah.
Okay.
Do you mean like the general direction of
yeah, so what's next for you? We are almost out of time, but maybe you can take 30 seconds to tell us where your research is headed next.
Yeah, sure. So basically, we are generally interested in this machine learning on graphs, right? Not specific to knowledge graphs. And we are interested in like how to design like more expressive models so that it can, let's say in this knowledge graph setting, it can not only like deal with this conjunction or union, you can also deal with negations, right? To make these models more expressive and also make this model more robust in the sense that it can deal with these adversarial or malicious attacks, especially in this like online, like in Amazon, right? There might be some customers or sellers can be malicious. And also like how to make the model more interpretable or explainable. I guess that's the overall 3 directions that our lab, right, try to pursue in the future directions.
Okay. All right. So with that, we are out of time. I will really like to thank you, all 3 of our speakers, for illuminating us with their different perspectives. And I feel really energized and excited about this whole knowledge graphs area. So thank you all for coming, and thank you all for your time. And for everyone in the class, we'll see you next week. Bye for now.
Thank you for involving me. This was fun.